Hi guys, let's look at this problem called round trip 2. So Zenithland has n cities and n cities and m flight connections. Your task is to design a round trip that begins in in a city, in some arbitrary city, goes through one or more other cities, and finally returns back to the starting city. Right? So that is the problem statement, and it says every intermediate city on the route has to be distinct, right? So that's the problem, and there are at most 10 test cases. N is bounded by 10 power 5, M is bounded by 2 into 10 power 5. And yeah, that's the problem. One thing to notice is um, I think, yeah, here it is given. All connections are one-way flights from a city to another city. So what it implies is the problem essentially gives you a graph. There are n nodes in the graph and m edges in the graph, and these are unweighted. But the thing is, the directions of these edges are directed. Like these are directed edges. These are not undirected edges, as you see in some of the other problems on graph. Because of this statement here, all connections are one-way flights from a city to another. Had it been all connections are bidirectional or two-way flight, something like that, um, then it would again depend on maybe if it were weighted, then we would have made weights on the graph and made two edges, two directed edges. But yeah, but for this question, we are just interested in because it just says it's a directed graph. That's all. Okay. Um, so if such a round trip exists, so the problem asks us to, it's basically an existence question that it does there exist a cycle in the graph? That's all. If there exists such a cycle or a round trip, then we would report yes, else we would like to report no. So let's take an example. Let's take this particular example only and see why the answer is yes. Okay, so I just drew the graph, and as you can see, the edges are directed, and this particular path, that is 2, 1, 3, and then back to 2, that forms a cycle, that forms a round trip. And because of this round trip, the answer is the output is simply yes, as you can see in the sample example as well. And therefore, it basically reduces to detection of cycle in directed graph. That's an important thing to note here. And one more thing to note here that they have not given that the graph is in a single piece, something like that. These can be disconnected as well, right? One component can be somewhere, the other component can be somewhere. Obviously, these components need to be directed. Uh, that is there, but then there might not be any connection between them. So that is one thing which is implicitly true, uh, and people generally do not like make it an assumption that okay, it's a single piece, and even if they would have coded it correctly, they would have missed this simple point. So such things just keep in mind that for general graphs, they need not be connected and solve the problem accordingly. Okay, so let's look at this example that same example. Um, so what like how would we detect the cycle in a directed graph? The algorithm is a bit different from how we would like to detect a cycle in an undirected graph, right? Um, in a directed graph, based on the traversal, we can based on the order in which the nodes are visited, it's generally called something called as a DFS tree, DFT. So one calls three, then three calls four, then four does not have any unvisited adjacent, so it gets popped out. Then it calls two, then then again two does not have any undirected adjacents, unvisited adjacent node. So that marks the termination. But obviously these nodes will be there, two, three, one. So we have to just simply pop them. So the tree that this type of traversal forms is called it's called a DFS tree, right? Um, and this DFS tree has some interesting properties. That is, the nodes that are called in the successive orders in the traversal are are essentially called as forward edges. Sorry, these are called tree edges. All these nodes are called tree edges, no matter uh, if you like the 2 to 4, that is also a tree edge. BE, the green one, that is also a tree edge. Blue one is also a tree edge. So these tree edges uh, can be further broken down into something called as forward edges. The ones that you see, the order in which they are traversed, uh, they are called forward edges. And then there is something called as a cross edge and a back edge. We will go over these in detail as we run the algorithm. But just a heads up. Anyway, we will be revisiting these concepts as we run this algorithm. So so imagine when we are calling a DFS on a particular node, it actually builds a stack within the tree stack, um, and then as we move in the recursion, uh, either the element gets popped or gets pushed based on some decision. So let's look at those decisions in more detail. And based on based on the traversal and the stack that we form, the states of the nodes can be divided into three categories. And so the state of zero of an arbitrary node is essentially it's not yet visited. The state of one means the node is currently in the stack, in the active stack. And the state of two is when the node gets popped out and it's no more in the stack, right? Um, so those are the meanings of the uh, the state array. Now let's run the algorithm. So first we visit one, it gets pushed because it was not yet visited. It was initially zero. So from zero uh, we will change the state to one and push it to the stack. Pushing is implicit because in code you would just call the recursive function. So that's equivalent to pushing it. Um, and then we will so from one we will go to three in the order of DFS. And because three was not visited earlier, so three gets pushed on top of one, and the state of three changes from zero to one. Moving further, three will call four, and again, the state of four changes from zero to one, and it gets pushed onto the stack. Now, for four, as you can see here, four has no uh, adjacent actually. There are no edges coming out of four, right? Therefore, we can see that for all the adjacent are correctly processed. So we can simply remove 4, we can pop it. That's the simple return statement that we see in code. So we just pop it, and because of this pop, the state changes from 1 to 2, right? because it's no more an active node, it gets kicked out of the stack. So that's important to note here. The state of 4 is 2. And then, um, so we had 1, and then we had 3, and then we had 4, right? Now, after this pop operation, we currently just have 1, 3. And then we are about to call 2, right? Uh, so once we call 2, yeah, 2 is also unvisited. So 2 will be called and it gets pushed, and the state of 2 changes to 1, right? Uh, like once state of 2 changes to 1, it further asks the question that does it have any unvisited neighbor? Well, the answer is no, but still it goes through that adjacent for loop in the code, right? We will see this in code again. Um, like both 4 and 1 are visited earlier, right? But these are different types of visits. Um, so for 4, when it sees 4, it says, okay, the state of 4 is currently 2. Remember, the state 4 was kicked out of the stack, so the state is currently 2. And this is a different category of edge here from 2 to 4, therefore. And these are called cross edge. That means 2 and 4, they are not in the same active path. So the active path here is 1, 3, 2. These three are currently present in the stack. 4 isn't currently present. But in the order of DFS, 2 to 4 is called. Because of this calling, this 2 to 4 edge becomes cross edge. One of them is currently in stack, the other is not in stack. That's the property of a cross edge. Okay. Uh, yeah, so that's there. It's not very important to solve the cycle detection question, but there are interesting properties of cross edges, and this is how you can detect cross edge in a directed graph. Okay. Now once for 2 asks for, then it will ask the other neighbor, which is 1. Now note 1 is currently present in stack, right? So here we are, 1 is currently present in stack, and the state of 1 is still 1, right? State of 1 is still 1, it's not changed yet. Um, and therefore, it's a different category of edge. This is, so 2, what 2 is saying, okay, there is a node which is present in my active path, and currently, so yeah, active path means sometime before, like if I trace back my ancestors, that node will be my ancestor. 1 will be my ancestor. But right now, due to this DFS call, rather not DFS call, due to this detection of a new neighbor, 2 says 1 is also my neighbor, right? So that means 2 happens to be a an ancestor as well as a descendant of 1. Um, because of these type of, so this is called backage. So we are going back to our ancestor. Um, and because of this detection, this actually presence of such a backage actually implies, in fact, it's a double implication that there is a cycle in the directed graph. And we can simply like simply notice this by looking at the state array of 1. State array of 1, and there is a edge from 2 to 1. These two information suffice to tell us that, okay, there is a back edge from 2 to this node 1. And that simply uh, detects the cycle. So we can now say that, okay, there is a cycle in the graph, and we can just like change the state of the exist flag from false to true, right? And we need to do this for all the components of the graph. It so happens that the input test case in the question is in a single piece. Maybe let's say you would have some 5, then 6, and then again to 5, something like this. We would have run this again on that, um, like let's say this particular graph was a directed acyclic graph, and then there was this 5 and 6, but these are, excuse me, these are these are disjoint. So we need to run this cycle detection again on 5 and 6. Um, yeah, so that's one thing to keep in mind. We will see that in code in greater detail. Okay, so hope the concepts are clear how to detect a cycle in a graph. So say cycle detection algorithm is pretty simple. We just like we call a cycle exist function, and all it does is it initializes the state array, right? This, yeah, this is equal to 0, and we just also initialize a variable exist equal to false. We want to know if there exists a cycle anywhere in any component of the graph. So we start with all the nodes. If those are not visited, so this particular step here implies that we are going over all the components, right? We are not missing any component, right? So if the state of some I is 0 for the first time, then we will start a DFS from there. We will send the exist flag. So this exist flag will be passed by reference because the return type of my DFS is void. I'm just passing it by reference so that I can track it for all the components. And the state variable that also needs to be passed. That implies the state of the stack. Um, State of a node in the stack. Is it present in the stack? Is it already kicked out, or is it yet to be pushed into the stack? So that information need to be passed. And after solving a subproblem, that is after solving one component, if the exist is true, right? We found a component where there exists a cycle. We simply early exit. We simply return true and early exit out of it. That suffices to say that there exists a round trip. And for all the components, if there never exists a cycle, all of them are DAGs, then we can simply say, okay, we can return false. We did not find a cycle in any of the components. And coming back here, this I have actually explained in slides in greater detail. So initially, when a node is called, the DFS is called, the state of the current in the stack changes from 0 to 1, and then we call, and then we go over all the adjacent nodes. If the neighbor is 0, yet to be visited, we recurse on it, and this is a forward edge, right? This current to neighbor is a forward edge, uh, and we recurse further starting from the neighbor node, and we pass the state array as it is. If the state of the neighbor is 1, that is, it was seen some, it is currently active in the stack, then that suffices to say that we have found a back edge, and also so it is sufficient to say that we have found a round trip, that is a cycle as well. So simply we make the pass by reference variable exist to be true. That's it. And for the cross edge, although we can detect it here using this else condition, but for this particular question, it does not carry any relevance. Okay. Finally, once all the adjacent nodes are taken care of, we just change the state of this current variable from active to inactive. So 2 means inactive, but this means it has been visited somewhere earlier, right? And then we just that's the code in like completeness. So you can give it a try and solve the question. So just be careful that we have to be doing this on all the components, not just a single component. And the complexity will be simply uh, order v plus e because this is a simple, this is simple DFS. It's just that we are going over all the components anyway. Uh, anyway, like we will go over all the nodes and basically all the degrees of the graph. Therefore, the complexity will be order v plus e. Okay, that completes the solution video for this problem. Thank you for watching.